Okay, we're continuing with chapter 12. In this video, we're going to go through the last section, which talks about, does the regression make sense? Okay, so what they're talking about here is you could have a case where there's a high correlation coefficient, close to 1. The data is football shaped, it is linear. You do a linear regression and you get a pretty low RMS, but the regression still doesn't make sense. And you might be thinking, okay, so we must be talking about the idea of association versus causation. Maybe the regression doesn't make sense from a causation standpoint, but it still makes sense from an association standpoint. Well, actually, no. It still might not make sense from an association standpoint as well. So how is that possible? Well, let's take a look. So it says a regression line can be put down on any scatter diagram. However, there are two questions to ask. First, was there a nonlinear association between the variables? If so, the regression may be quite misleading. So, yeah, that is one case where the regression might not make sense if it is, in fact, a nonlinear association. So you could still get a decent correlation coefficient, but the data isn't linear. So, right, this you want to curve fit with something like an exponential. But, I mean, you could still do a linear regression and the RMS would be okay, right? But it's still not applicable for a linear regression. It's not ideally applicable for a linear regression. And then obviously something like this isn't linear, right? You would want to curve fit this with something like a quadratic. And you'd probably see this manifest itself with a higher RMS error. So the first thing they're pointing out is, does the regression make sense from the perspective of, is the scatter plot linear? Which we've talked about the way to test for this. The ideal way to test for this is to see if the data is football shaped. Is it elliptical? Is it homoscedastic? Okay, but what we're really talking about here, more importantly, is, so even if the association looks linear, so even if it is football shaped, there's a second question. Did the regression make sense? The second question is harder. Answering it requires some understanding of the mechanism which produced the data. If this mechanism is not understood, fitting a line can be intellectually disastrous. So you might be scratching your head thinking, well, man, how could it be possible that you could have football-shaped data with a high correlation coefficient? You do a linear regression, there's a pretty low RMS. How could there, at the very least, not be an accurate association there? And in general, you're absolutely right. Okay, so let's look at this example that they give, and then we'll clear up any confusion that you have regarding the whole association versus causation. Because I know when I first learned this, I found this a little bit confusing as well. So it says, to make up an example, suppose an investigator does not know the formula for the area of a rectangle. He thinks area ought to depend on perimeter. Taking an empirical approach, he draws 20 typical rectangles, measuring the area and the perimeter for each one. The correlation coefficient turns out to be 0.98, almost as good as Hooke's law, which we worked with in the previous section. We did a linear regression with, we hung masses or weights from a spring and then plotted the deflection of the spring versus the weight, which we know is a linear relationship. But we're getting a correlation coefficient here that's almost as good as what we got with Hooke's law. The investigator concludes that he is really on something. His regression equation is, so the area of a rectangle, and here's the formula with the input being the perimeter of the rectangle. Area is measured in square inches and perimeter in inches. So perimeter is in inches here, so the resulting units are square inches, which is what we expect for area. All right, so if we come here, here's the scatter plot, and you know that's definitely football shaped, right? This applies to a linear curve fit. This data is homoscedastic, football shaped, and you could see it's clustered around a line. This is exactly the only regression you would use for this would be linear regression. So you have a high correlation coefficient. You're going to have a low RMS, And this is football shaped. It is linear. So how could we possibly be saying that the association is inaccurate? Maybe the causation, but how could we be saying the association is not accurate? Well, the reason is because there's not enough data points here. They didn't do this for a big enough span of different sized rectangles. That's the reason. Okay, so I made an Excel sheet and plotted a lot more different sized rectangles and determined the area of a much larger span of different sized rectangles with different aspect ratios, really wide and thin rectangles, really tall and skinny. Okay, and then made a scatter plot of the perimeter versus the area. Okay, so you've got I just did a random integer between 1 and 500 for each of the length and width columns. Perimeter was just 2 times the length plus the width. Area was the length times the width. And then just plotted the scatter plot of the area versus the perimeter. So there's like over 750 rectangles, and there you go. Right? In general, the relationship between the area and the perimeter of a rectangle is not linear in general. Now, yes, if you focused on a small group of specifically sized rectangles with specific aspect ratios, then okay, you get like a linear relationship in this sense in this region, right? But in general, no, it's not a linear relationship. And so that's what they're referring to here. So like, yes, if you wanted to be more specific and say something like for rectangles with this aspect ratio, so that would be like the length divided by the width, there's a linear relationship, then maybe you can say something like that. But in general, for what this investigator is talking about, just a general formula for the area of a rectangle based on the perimeter, you cannot make the statement that there is a linear association with like correlation coefficient 0.98 between area and perimeter. That's what they're trying to illustrate here in this section. So it says there is a scatter diagram in figure 6 with 1 dot for each rectangle. The regression line is plotted too. The rectangles themselves are shown in figure 7 on the next page. The arithmetic is all in order, but the regression is silly. The investigator should have looked at 2 other variables, length and width. These 2 variables determine both area and perimeter. So yeah, maybe the investigator, if we come to the next page, so here's the 20 rectangles that the investigator measured. So you're in this aspect ratio range. So you could maybe say for an aspect ratio near whatever these aspect ratios are that you have a linear relationship. But if you're really trying to come up with an all-encompassing relation for the area of a rectangle based on its perimeter or based on some features of the rectangle, then maybe he should have plotted the area versus the length as well and the area versus the width as well. And maybe the perimeters versus the lengths and the widths, right? Done a more thorough investigation. Because we know that, so area and perimeter are both functions of the length and width of the rectangle, but one is non-linear and the other is linear. Okay, so it says, when looking at a regression study, ask yourself whether it is more like Hooke's law or more like area and perimeter. Of course, the area perimeter example is hypothetical, but many investigators do fit lines to data without facing the issues. That can make a lot of trouble. Yeah, so I don't know how you would, if you're doing a regression study, how you could figure out if you're dealing with something that's more like the Hooke's law or the area and perimeter problem. I say that because, yeah, it's easy that since we know in hindsight that area is non-linear in terms of length and width, but in a real study, you wouldn't know this. So to me, what this, the big lesson to be learned here is you have to really notice if you're only studying a subset of all of the possibilities of something, right? If we come back here, you have to look at this and say, okay, this is fine, but what if the rectangles are, why don't you include some really, like, I'm not saying you have to test 1,000 rectangles necessarily. I mean, ideally, I guess you test 1 billion rectangles, right? But like, there's got to be some sense of being efficient with studies. So why didn't you include, if you're going to just test 20 rectangles, why not include one that's really, really wide and thin? And then one that's really tall and skinny. Right? With the 20 rectangles you pick, why not try and encompass the full range of all possible rectangles? Now, if you did this, there would still be kind of the question of, well, what if it was really, really wide and short? Right? Really wide. Maybe at the extreme ends, it tapers off. Yeah, maybe so. But still, if you're going to do a more short, comprehensive study, still, to me, this is a poor design with just 20 rectangles. At the very least, you want to try and capture the full range of the characteristics of whatever you're studying. And if they would have done that, they would have noticed, okay, it's not linear. Okay, now, I just want to note that in this section, we're just barely scratching the surface of analyzing if regressions make sense. In more advanced statistics playlists that we'll do, we'll really dig into analyzing regressions, residual plots, the works. So right now we're just getting a sense of this. Okay, technical note. Example 1 in section 1 presented a regression equation for predicting income from education. This is a good way to describe the relationship between income and education, but it may not be legitimate to interpret the slope as the effect on income if you intervene to change education. The problem, the effects of other variables may be confounded with the effects of education. Yeah, we talked about this. It's, in particular with observational studies, you can't look too deeply into a regression line or a curve fit. The more potential confounding variables there are, then the less you're able to kind of think outside the box or just think outside the strictly, okay, the regression line was created for these data points and these data points only. Or try and make predictions about what's going to happen, or make predictions like they're talking about if you intervene to kind of change a variable or adjust a variable and predict what would happen. Right? The issue with doing this with observational studies is the confounding variables. So in this case, the effects of other variables may be confounded with the effects of education. Right? You didn't decide who was in the treatment and control groups. The people that have less education might have less education they're not as ambitious, right? They're, maybe they're criminals or something. I don't know. Have mental issues, whatever. Or maybe the people that have more education, that are making more money, are criminals. Again, you're not controlling who's in the treatment and control groups. That creates more confounding variables. Okay, so it says, well, many investigators would use multiple regression to control for other variables. For instance, they might develop some measure for the socioeconomic status of parents and fit a multiple regression equation of the form. So, yeah, so you think about potential confounding variables and you do a more complex regression that accounts for these variables. So they're talking about this multiple regression here. It's still a linear regression, but you have additional variables added into it. So you've got the educational level as well as the measure of parental status. And you're doing this. This is a linear equation with these 3 coefficients you need to solve for. Okay, so it says that the coefficient B would be interpreted as showing the effect of education, controlling for the effect of parental status. Yeah, so what they're saying here is this coefficient B, you're going to determine these 3 coefficients simultaneously. So the coefficient B is going to be higher or lower in conjunction with whatever the coefficient C turns out to be, right? These coefficients are all going to be decided together at the same time. So it's saying, well, look, without the measure of parental status, this coefficient might be 0.92, but when you add in the measure of parental status, this turns out to be 0.85. So it's considering the effect of the parental status. So B is showing the effect of education, controlling for the effect of parental status. All right, now it says this might give sensible results, but it can equally well produce nonsense. Take the hypothetical investigator who was working on the area of rectangles. He could decide to control for the shape of the rectangles by multiple regression, using the length of the diagonal to measure shape. Of course, this isn't a good measure of shape, but nobody knows how to measure status very well either. The investigator would fit a multiple regression equation of the form: the predicted area is A plus B times the perimeter plus C times the diagonal length. He might tell himself that B measures the effect of perimeter, controlling for the effect of shape. As a result, he would be even more confused than before. The perimeter and the diagonal do determine the area, but only by a nonlinear formula. Multiple regression is a powerful technique, but it is not a substitute for understanding. Okay, yeah, so really, when it comes to this investigator investigating the area of a rectangle, he would really need to analyze the relationship between like length and area and width and area and figure out that it's a nonlinear relationship he's dealing with. He's spinning his wheels by trying to come up with some linear relationship for the area of a rectangle. Now, it's not like he potentially couldn't come up with a linear formula like this. If he controlled for enough variables, then, eventually it would work, right? Maybe if he controlled, instead of diagonal, he made this the aspect ratio. Okay, but in reality, what the investigator wants to do is figure out that, hey, the more appropriate relationship here between the area and the dimensions of a rectangle is this nonlinear relationship between the dimensions of the rectangle and the area of the rectangle. And so really the desired outcome is figuring out that this is the case as fast as possible. All right, and so again, in this section, in this course, we're not going too deep into studying whether or not regressions make sense and how to see if it's linear, nonlinear, etc. That's for more advanced statistics courses. But right now, we're just trying to get a sense of analyzing regressions. Okay, now, and also they're talking about this multiple regression here. That's also a more advanced topic for more advanced courses. Okay, so now in the next video, we're going to go through these end of the chapter review exercises.